In classical machine learning, adding too many parameters to a model is a recipe for disaster. If a system has more parameters than training data, it memorizes the noise instead of learning the underlying pattern, leading to catastrophic overfitting. This principle is captured by the bias-variance trade-off. This chart plots model complexity on the x-axis against test error on the y-axis. As a model grows larger, its error decreases up to a point, before inevitably spiking upward as the model becomes too complex. But modern deep neural networks break this rule. If we continue adding parameters beyond that peak, pushing the model into massive overparameterization, the test error drops back down into a second descent. That volatile peak is known as the interpolation threshold. At this exact point, the network has just enough capacity to fit noisy training data perfectly, resulting in maximum sensitivity and maximum error on unseen test data. The mechanics behind this second drop provide the groundwork for moving deep learning from a heuristic practice into a predictive science. One of the earliest mathematical frameworks attempting to explain how massive networks manage to generalize was the information bottleneck theory. The core claim of the information bottleneck theory is that neural networks go through a distinct compression phase. The network acts as a funnel, actively discarding high-entropy, irrelevant data from the input layer by layer to isolate a clean target signal. According to this theory, optimization happens in two steps. First is a drift phase, where the network memorizes the data. Second is a diffusion phase, where the noise inherent in stochastic gradient descent forces the network to compress and shed task-irrelevant information. The idea of a network actively deciding to forget is an elegant narrative. But as researchers began mapping the exact statistical topography of these networks, they discovered that this compression phase is an illusion. A major study by Sachs and colleagues tested the information bottleneck theory by calculating the exact trajectories of different neural architectures as they learned. This chart plots the network's trajectory. The x-axis measures information with the input, the y-axis with the output. Networks using a Tanh activation function match the predictions. The trajectory hooks sharply to the left, representing a mathematical loss of mutual information with the input. The researchers then ran the exact same experiment, but swapped the Tanh activation function for the industry-standard ReLU function. In the ReLU networks, the compression phase vanishes. Looking at panel B, the trajectories move steadily up and to the right. There is no leftward hook. Even without dropping any mutual information about the input, the ReLU networks achieved identical or superior generalization performance on the test data. This result severs the causal link between information compression and test performance. The networks learned the target without shedding the input data. The compression phase is a geometric anomaly triggered by the shape of the Tanh activation function, rather than a universal requirement for deep learning. Why exactly does Tanh create this mathematical compression, while ReLU does not? To calculate mutual information, researchers group continuous neural network data into discrete intervals, a process called binning. The Tanh S-curve flattens horizontally at extremes. As weights grow, varied data points are pushed onto these flat ends and forced into the exact same bin. When distinct inputs are squashed together into a single bin, the measured entropy of the system artificially drops. It looks like the network is forgetting information, but the data is just saturating the bounds of the function. ReLU, on the other hand, is linear and unbounded on the positive axis. Positive data points spread infinitely outward, populating new bins. The measured information never drops. The information bottleneck theory also claimed that the randomness of stochastic gradient descent is what forces the network to compress this data. Yet, when researchers trained Tanh networks using full batch gradient descent, a method that uses the entire dataset at once and contains zero randomness, the exact same compression hook appeared. Neural networks do not actively shed irrelevant information to achieve generalization. The famous compression phase was a statistical mirage caused by activation saturation combined with a discrete binning methodology. If compression isn't the mechanism, how do networks with billions of parameters avoid overfitting the data? The answer lies in the field of learning mechanics, which models training as a trajectory through a high-dimensional, non-convex loss landscape. In highly overparameterized models, the landscape changes. There is no longer a single optimal solution, but infinitely many global minima that achieve zero error on the training data. Some of these solutions are sharp minima. In these narrow spikes, even a tiny shift in the network's weights causes the error rate to catastrophically spike. The other solutions are flat minima, and their advantage is explained by the volume hypothesis. Flat minima occupy exponentially more volume in the parameter space. Because they are physically wider in this geometric model, they are statistically much more probable destinations for the network to find. This is where the noise of stochastic gradient descent actually plays its part. The random variations in each mini-batch act as a form of kinetic energy. This kinetic noise continuously kicks the parameters out of the narrow, sharp basins. The model bounces around the landscape until it settles into a wide, flat, degenerate basin, where the noise is no longer strong enough to push it out. These flat minima act as an implicit regularizer. The network generalizes because it naturally settles into a mathematically wide, noise-tolerant state, completely independent of compressing or forgetting the input data. We can map this geometric landscape directly to the physical size of the network, using principles from statistical mechanics. Physicists describe network capacity through the jamming transition, a concept originally used to explain how granular materials behave under pressure. When a network has too few parameters, the system is jammed. It is mathematically stiff, heavily constrained by the data, and easily trapped in sharp local minima. Adding excess parameters unjams the system. The model gains the mathematical degrees of freedom required to move fluidly around the data constraints. This added fluidity is what allows the optimization path to bypass the sharp spikes and flow cleanly into the wide, flat valleys that produce good generalization. Massive scaling alters the physical phase state of optimization, turning a rigid trap into a fluid flow. The objective of learning mechanics is to take these physical descriptions and use them to predict network behavior at massive scales without relying on empirical trial and error. Researchers do this by studying networks in the infinite width limit. As the width of the layers approaches infinity, the random fluctuations disappear and the signal flow through the network becomes entirely deterministic. Standard parameter scaling causes signal variance to explode as models grow, but a framework called maximal update parameterization, or MUPI, solves this. By scaling weight initializations and learning rates according to specific mathematical rules, the network's internal activations maintain a stable, predictable variance, regardless of how wide the layers get. This results in a technique known as mu transfer. Engineers can tune their hyperparameters perfectly on a cheap, small proxy model and instantly deploy those exact settings onto a massive frontier model with no additional testing. Neural networks are physical systems governed by exact laws, functioning independently of any cognitive desire to forget. Mastering their statistical mechanics enables the engineering of the next generation of artificial intelligence.